Hey guys, today we're talking about section 13B, exponential and logarithmic equations, but this is the inequalities part. This is a pretty short section, so stay with me, okay? So if we're talking about inequalities, remember we also have to talk about what can work for values of x in a log. We call this part, by the way, whatever's inside the log, we call that the argument, okay? So remember that the argument of a log has to be greater than 0. So what are the restrictions of the arguments of these logs? So we know x minus 8 has to be greater than 0. 2 only has one value, so we don't have to worry about that. The other argument, 3x plus 4, also has to be greater than 0. So if I solve these, I know x is going to be greater than 8 on that left side. If I subtract over the 4, divide the 3, I get x has to be greater than negative 4/3, okay? If I put these on a number line, here's negative 4/3, here's 0, here's 8. This looks like this, and the 8 looks like this. The one that is really more restrictive is the 8. So this is the one that I'm going to focus on, okay? So if out of the restrictions for those arguments, the one that really makes the most difference is that we know that whatever x is, it does have to for sure be bigger than 8. Because that's the most restrictive one. So now let's go ahead and solve and compare the intersections of that example. So let's go ahead and solve it. So if I'm looking at this, I'm going to put this right here, okay? So log of x minus 8 plus log 2 is less than or equal to log of 3x plus 4. So we're going to use that product rule to condense these two logs down to one log. So here's log of x minus 8 times 2 is less than or equal to log of 3x plus 4. Okay, and then we know if we raise both sides by a 10, or we know that property if you have the same base log on both sides, so they're equal to each other, so the arguments are also equal to each other. We can say 2 times x is 2x, 2 times negative 8 is negative 16, is less than or equal to 3x plus 4. We can go ahead and solve for x, so subtract the 2x over to get x's like terms together. Subtract the 4 to the other side, so we end up with x on the right side and negative 20 on the left side. We usually like to have the x on the left side, so if I flip this around, this also will switch. So I get x is greater than or equal to 20, but remember, our argument said that x has to be bigger than 8. So because this is the most restrictive, this is going to overtake the solution that we found, and we know that whatever goes inside that x has to be actually bigger than 8. Because if I put this on a number line, if here's negative 20 and here's negative 8, they're both going to the right like this. In order for these values to work, we see the overlap is right here where x is greater than 8. So that's actually the overall solution. Let's go ahead and try this one, okay? So when we're trying this one of the things I want you to highlight, okay, is that when we're changing from a logarithmic to exponential, the argument stays on the side that it started with, okay? So there's kind of a clue. So one of the ways that we can cancel out a log is by turning this into exponential form. But keep in mind, the argument is staying on the left side of the inequality here. So here's our inequality. So we know left to the right equals the middle. So we're going to put the left to the right on this side, and 2x plus 6 goes here. Because this is the argument, it has to stay on the left side of the inequality. Keep in mind, we also have to look at the restrictions of the argument. And that means that 2x plus 6 also has to be greater than 0. So if we solve that, we get x has to be greater than 3 is one of our restrictions. So let's go ahead and solve this out and see what we get. So I know 2 to the third power is 8. 2x plus 6, let's solve. Divide both sides by 2. And we get x is greater than 8 minus 6 is 2. Divided by 2 is 1. So let's look here. Let's compare. So here's our restriction and here's our solution. If I put this on a number line, here's negative 3. So if x is greater than negative 3, it's going to look like this. Whereas this is x has to be greater than 1. So 1 would be here. So we see that they overlap right here. Therefore, this is our solution because that's the most restrictive one. Let's see what happened. What would happen if this was less than instead? So let's just kind of see what would happen there. So if it was less than instead, the restriction on the argument would be the same. So we would still say x still has to be greater than -3 because if that's the restriction on the argument. But if this was less than, that means that this sign would change. That when I solved this, instead of it being x is greater than 1, the solution would have given x is less than 1. So let's put that on the number line. If here is x equals -3, just like before, it would look like this. But the solution, x is less than 1, here's 1, and it would be to the left. So we see that overlap here in the middle. So this here is our solution. So therefore, x would have to be between, would have to be between -3 and 1. And in interval notation, we would say that it goes from -3 to 1. Same thing here. If we were to solve the first time and put that in interval notation, we know that it would have to be from 1 to infinity in interval notation. Okay? So let's work on example number 3. So do exponentials have restrictions on their domains? The answer is no, because when we're talking about exponents, those domains can be anything, including negatives and zeros in the exponent. So you're good to go. So let's go ahead and solve this one. So here I see 3 to the x plus 2 all minus 4 greater than 23. So because there's no restriction, we can just go straight into solving. I know we're going to add that 4 over here so we can get that base number to its exponent on its own. Now, the way that we're going to cancel out the 3 is by taking a log base 3 of both sides. So this cancels. This is x plus 2 on the left side and then log base 3 of 27 on the right. I know that 27 and 3 have a relationship, so I can rewrite log base 3 as 3 to the third because 27 is equivalent to 3 to the third. Remember that log base 3 and 3 can cancel, so we're left with 3 on the right side and x plus 2 on the left. Go ahead and solve, and we get x has to be greater than or equal to 1. If I was going to put that in interval notation, if this is 1, it's going to look like this. So we're going to say it goes from 1 to infinity. Okay, let's talk about finding the inverses. So remember, the inverse is always the same 4 steps. Find your y, swap your y and your x. Whoops. And now we're going to solve for y or get y alone. So in order to get y alone here, because it's up here in the exponent, we're going to have to move everything away. So let's add that 4 over, just like reverse PEMDAS that we've been using to solve for equations. Divide by the 3. So I end up with x plus 4 over 3 equals 2y plus 1. And then here, in order to get this exponent out of there, we're going to take a log base 2 of both sides. So this is going to cancel. We end up with y plus 1 equals log base 2 of x plus 4 all over 3. Subtract the 1 from both sides. So I've got almost done. And then this is where I rename my y as the inverse of f of x. Okay, and that's how we find our inverse. Go ahead and pause the video right now and try the next one, example 5, on your own to find its inverse. All right, I'm hoping that you actually tried it. Let's see if you got it right. So again, you were supposed to try this and hit pause because this is how you grow. Okay, let's check it. So if this is y, now we're going to switch the x and the y and put everything back. Now we're going to get y by itself. So we're going to subtract that 10 over. And let's take care of that ln. So we're going to raise everything by an e. Subtract the 3. And so we end up with 2y equals e to the x minus 10, all subtracted by 3. Divide both sides by 2. So we've got the inverse of f of x equals e to the x minus 10 power, all minus 3 divided by 2. All right, we'll see you in class.